Hello, today we're going to go over exponential and logarithmic equations. That is section 4.4 from our book. So we're going to be looking at equations that involve exponents and that involve logarithms, and we're going to look at strategies for solving for missing variables. So the first ones we're going to look at are solving exponential equations. So we want to make sure we rewrite the same base on both sides of the equation. So essentially the base has to be the same. So if I have two sides of the equation where the base is the same and they have exponents, then the exponents must be equal to each other. That's the general gist of what this is saying right here. So in the first example, 1a, we have 2 to the x minus 4 equals 2 to the 5th. They have the same base of 2. Therefore, their exponents must be equal. So x minus 4 must be equal to 5. We just solved that equation, and we end up getting that x is equal to 9. On C, B is on the next slide, so we're going to look at C. On C, the bases are not the same, but we can actually rewrite 8 and 4 as powers of 2. So it kind of takes some creative number sense and number logic to figure out how to rewrite these. So 8 is the same thing as 2 to the 3rd, and 4 is the same thing as 2 to the 2nd. And then we're going to put those to the power x plus 3 on this side, and this one was 5 minus 2x. We then use our laws of exponents and the power rule to get that this is 2 to the 3x plus 9, and this side will be 2 to the 10 minus 4x. Now we have the same base on both sides, so their exponents must be equal. 3x plus 9 must equal 10 minus 4x. We're going to get the x's on one side and the constants on the other side. So we end up getting that 7x equals 1. So x equals 1/7. In this example, B, we have 5 to the 3x minus 1 equals 125. We can rewrite 125 to be in terms of 5 to a power, and that's the same thing as 5 to the 3rd power. So we get 5 to the 3x minus 1 has to equal 5 to the 3rd. Therefore, the exponents must be equal since the bases are the same. So I get 3x minus 1 equals 3. So that gives us 3x equals 4, so x is equal to 4/3. And then on this last one, we have d is 1/4 is equal to 8 to the x. So I can rewrite these in terms of powers of 2. 1/4 is the same thing as 2 to the negative 2nd power. That negative power kicks that down into the denominator, and 4 to the 2nd power, 2 to the 2nd power is 4. And then this is the same thing as 2 to the 3rd to the x. So that means that 2 to the negative 2 equals 2 to the 3x. Same base, so our exponents in this case must be equal to one another. So we get negative 2 equals 3x. So x is going to be equal to negative 2/3. Our next type of equations are a little bit different because if you look at the first example, A, we have 2 to the x equals 7. Now there's no easy way to rewrite 7 in terms of a power of 2. So our method that we saw in the last examples will not work. So in these kinds of situations, we actually want to take the logarithm of both sides of the equation. We're allowed to do that because it's consistent. We've done the same thing on both sides, which keeps it equal to one another. And then we can use the power rule of logarithms to actually take our exponent within the logarithm and kick it out to the front of the log. So let's see this in action. I have 2 to the x equals 7. So I'm going to take the log of both sides. So I get log of 2 to the x equals log of 7. By the power rule, this is the same thing as x log of 2 equals log of 7. So then by solving for x, we're going to divide both sides by log of 2. Now remember, log of 2 is just a number. That's something we can plug into our calculator. So x is actually going to be equal to log of 7 divided by log of 2. If I calculate that in my calculator, we get, rounded to the nearest hundredth, which is the second decimal place, 2.81. It's actually 2.807, so rounded it would be 2.81, and I'm actually going to make that an approximate because it's not equal to. We're going to follow that same process for letter C right here. We have 3 to the negative 0.002x equals 0.07. Now again, there's no way I can easily rewrite 0.07 in terms of base 3, so therefore I'm going to take the log of both sides. So log of 3 to the negative 0.02x equals log of 0.07. Okay, now again, based on our power rule, that's the same thing as negative 0.02x log of 3 equals log of 0.07. I'm going to divide both sides by negative 0.02 times log of 3 to cancel out both of those. So that will cancel and that will cancel, leaving me with x. But then I have to divide this side by the same thing, negative 0.02 log of 3. So let me rewrite log so we can see that easily. So x is going to be equal to 121.03 when rounded to the nearest hundredths place. Now, one thing to note here, I can check my answer. If I come to the original problem and I substitute 121.03 in for x here, so I would do 3 to the negative 0.02 times 121.03, I would end up getting 0.07 or something very, very, very close to that. Now remember, because we're rounding, we might just be close to it and not exact. Okay, so we're going to do 2 more problems. We're going to do letter B right here. Again, I can't easily put 8,000 in terms of 10 to a power, so therefore I'm going to take the log of both sides. Log of 10 to the x equals 8,000. The power rule kicks that x to the front. And we'll see here that we end up getting x log of 10 equals log of 8,000, but log of 10, that goes back to our basic properties. Log of 10 is the same thing as just 1, because my base here is a 10. 10 to what power gives me 10? That's 1. So we end up having that x is just equal to log of 8,000. When you calculate that, you get, rounded to the nearest hundredths place, 3.90. And then this last one, D, we have here 4 plus 3e to the 2x equals 11. So the first thing I actually want to do is I want to get rid of, or I guess move the 4 to the other side and divide both sides by 3 just so I don't have to worry about those aspects. I'm also going to use, instead of log base 10, which I've been using on all the other problems, I'm actually going to use the natural log because in this problem we're dealing with an e. So first thing I'm going to do is move the 4 to the other side. So we end up getting 3e to the 2x equals, what would that be, 7? Okay, and then we're going to divide both sides by 3. So we're just left with e to the 2x equals 7/3. Now I'm going to take the natural log of both sides. So I'm going to have the natural log of e to the 2x equals the natural log of 7/3. The power rule tells us that that's the same thing as 2x natural log of e equals natural log of 7/3. Now, the natural log of e is just like in the previous problem. It's the same thing as 1. So that goes away and we're left with 2x equals the natural log of 7/3. So we're going to divide both sides by 2 to solve for x. When we do that, we're going to do natural log of 7/3 all of that divided by 2, and that will give us our result. And our result rounded to the nearest hundredth is 0.42. So hopefully you can see that if I cannot easily change the bases on both sides of the equation to be equal to one another, then I will use this strategy of taking the log of both sides to solve for the missing variables. Please watch part 2 as we look at more examples of solving equations with exponential and logarithms.